This video discusses the normal curve covered in Chapter 5. Gauss, an astronomer and a mathematician, was measuring the path of planets. He found the errors in his measurements were not uniform, but tended to follow a bell-shaped curve. Many data sets exhibit this same quality. The normal curve is symmetric around the center and has one mode. The median equals the mean equals the mode. With one mode, we say the distribution is unimodal. If we toss a coin, we can measure the number of heads, or the percentage of heads. By repeating the experiment 3,000 times, we can create a histogram of the outcomes. We can see the histogram is approximately bell-shaped like the normal curve. Let us look at the normal curve with the median and standard deviation illustrated. Again, note the high point of the curve is the mode, m0, and the mean x bar is equal to the median, md, is equal to the mode, m0. We have also included lines indicating 1, 2, and 3 standard deviations below and above the mean. The area under the curve represents probability. Note 47.72% of the area is under the curve from the mean to 2 standard deviations above the mean, and 49.87% from the mean to 3 standard deviations above the mean. In figure 5.5 we have various areas calculated. From 0 to 1 standard deviation we have 34.13%. From -1 to +1 standard deviations from the mean we have 68.26%. We say that 68.26% of the area is within 1 standard deviation of the mean. Similarly, 95.44% is within 2 standard deviations of the mean, and 99.74% is within 3 standard deviations of the mean. We can calculate percentiles too. The percentile of a value is the area to the left of it. The area to the left of 1 standard deviation above the mean is 0.13% plus 2.15% plus 13.59% plus 34.13% plus 34.13% or 84.13%. Rather than using the original data or x values, we sometimes use standardized values called z-scores. The z-score is calculated by subtracting the mean and dividing the result by the standard deviation. Suppose the population has a mean mu of 100 and a standard deviation sigma of 15. We wish to find the z-score for a value of x equal to 130. First subtract the mean, mu equal to 100, from our value of x equal to 130 to get 130 minus 100 is 30. Then divide the result by the standard deviation, sigma equal to 15, to get z equal to x minus mu over sigma, which is equal to 130 minus 100 over 15, that is 30 over 15 or 2. Hence the z-score for a value of x equal to 130 for a population with a mean of mu equal to 100 and a standard deviation of sigma equal to 15 is 2. Now consider an x value of 122. The z-score is z equal to x minus mu over sigma, which is equal to 122 minus 100 over 15, or 22 by 15 equal to 1.47. Areas under the normal curve are given in Appendix A at the back of the book. The table gives 2 values. The first is the area from 0 to z, where z is a positive value. The other value is the area from z to the end of the curve. We can manipulate other values by using the symmetry of the curve. We take the following steps to find an area. Look down column 1 until you find the z value you are looking for. 2. Move to the right to column 2 to find the area between 0 and the z value. Move right once more to column 3 to find the area from the z value to the end of the curve. Consider the example of a value of x equal to 122 from a population with mean 100 and standard deviation 15. The z-score was 1.47. From column 2, the area from 0 to 1.47 is 0.4292. So 42.92% of the area lies between 0 and 1.47. From column 3, we have a value of 0.0708, so 7.08% of the area lies to the right of 1.47. Note that the two areas sum to 0.5. By symmetry, the area to the right of 0 is 0.5, and the area to the left of 0 is also 0.5. The total area is therefore 1. Thank you for watching. In the next video tutorial we cover the sampling distribution of the mean.